I'll simply thank you all for coming back. It's very nice of you. Okay, so basically I wanted to move on to the study of geodesics and their focusing, but there are a few things that I do need to continue with from the morning, and so I'll just do them quickly and then we'll move on. So we talked about a Cauchy hypersurface, and now there's a nice concept which is a Cauchy horizon. And this is the first time this important word comes into the discussion. And the definition of a Cauchy horizon is basically take a space like a coronal, yes. So take an acoronal space like hypersurface, S, and then consider its future domain of dependence. Now, as we've learnt, if the space-time is globally hyperbolic, then this plus the past domain span the entire space-time. But suppose it's not globally hyperbolic, or suppose this isn't a Cauchy surface, then let's consider d plus of S, and let's take its closure, add its limit points, and then let's look at the boundary of that. So the future domain of dependence of any hypersurface S, that's acoronal and space-like, and then look at the boundary of its closure, if there is any such boundary. So if there is such a thing, then it's called a Cauchy horizon. And fortunately for me, an illustration is already there in this figure. If I take this sigma, I'll call it S now. It's not Cauchy, but it's certainly space-like and acoronal. And d plus of S is this shaded region between the hyperboloid and the past light cone. Now you can clearly see that d plus has a boundary, and that boundary is the past light cone. So this plus this is the Cauchy horizon in this example. So it's the Cauchy horizon of that particular surface. And the definition is very natural, because a horizon should be where something ends, something doesn't continue, and in this case it's where the dependence of S ends. So S, you cannot go beyond that horizon and have things that are in the domain of dependence. Everything out beyond the horizon is outside the domain of dependence of this surface, which is not a Cauchy hypersurface. If it were a Cauchy hypersurface, then of course d plus would have no boundary, because it would be all of the future part of M. So the horizon exists exactly when you have surfaces that are not Cauchy hypersurfaces. Yeah? Was there a question? Yeah. Okay. So that's one interesting example. Okay, there's one, so I should tell you that historically, and I'll talk a little about the history of global hyperbolicity and the definition. Garrosh and Hawking, so this is a nice year, 1966. There's a nice short paper of Hawking in Physical Review Letters called something like Singularities and something, and then there's a follow-up paper to it by Garrosh in the same issue that starts at the end of Hawking's paper. So this is like 3 or 4 pages, and this is another few pages. And you can really read them as one paper, because each of them refers to the other, and sort of Garrosh worked on what Hawking was thinking about. And together they talked about possibilities of things not being globally hyperbolic. So if something's not globally hyperbolic, what should it at least be in order to have any kind of decent physics going on? And there is a weaker condition. So Hawking's paper actually is written in the style of, so I'll come to actually this paper when I talk about Hawking's Singularity Theorem, but that's not now, that's in the next, or that might be later today or in the next lecture. But he's like, under conditions 1, 2 and 3 we have a singularity, of which condition 1 would be Cauchy, globally hyperbolic. Then he would say, but if not 1, then under conditions 2, 3 and 7 we still have a singularity. So he has like 7 conditions and multiple combinations of conditions which ensure singularity. So that's really how he worked. He listed many different conditions and combined them into singularity theorems. And one of the conditions was what he called strongly causal. And so this is something that is weaker than globally hyperbolic. So I'll always use GHY for globally hyperbolic. And so a space-time is globally hyperbolic if for every point P and an arbitrary neighborhood O, there is a sufficiently small sub-neighborhood So to be a sub-neighborhood, V should be in O and P should be in V, through which no causal curve passes more than once. So earlier we showed that if you have a Cauchy hypersurface, then of course no causal curve. So there are no closed time-like curves and there are no causal curves passing more than once through a given region. But here we don't assume global hyperbolicity, but just strong causality, which is the precise statement that if I have, so I start with P, you give me a neighborhood O, I will find a sub-neighborhood V which is entirely inside O and contains P, and if there's a causal curve passing through it, that causal curve never for any reason passes out of it and back into it, so passes through it only once. So this is called strongly causal. And yes, so O is what is given to me. So the point is that whatever neighborhood I start with, there's a sub-neighborhood in which every causal curve passes only once.
Is that something required? That isn't every hyperbolic?
It's not globally hyperbolic, so I haven't ruled out. Yeah. Yeah.
Since you anyhow take a smaller neighborhood,
Yes.
what is the importance of O?
I guess that my smaller neighborhood should be contained in O. So however perversely I choose O, there should always be a smaller neighborhood inside it. You know, I might choose O to be so bad that, you know, this happens. So here's a causal curve. And
You can always make a tiny neighborhood.
maybe I'm okay. Let me think about this. I will tell you if I'll tell you if that's true. I'm not sure. I think there is a difference because it might be a different one. Okay, you're saying that there should be once and for all a neighborhood of P, and then it will be in every neighborhood O that I might choose. No, that's the problem. So if I ask you to choose a V, you'll choose a V, and then I can choose some O like that, and maybe this happens. So
Yeah, but if I can always go.
okay, let's do this later. Yeah. Okay, let me tell you the consequence of this definition, and then we'll discuss. No, it's not globally hyperbolic. That's the whole point. So strongly causal is weaker than being globally hyperbolic, and it's and I'll also tell you what it achieves. So what it achieves is that strongly causal implies no nearly closed time-like curves. So a nearly closed time-like curve would be a curve that's all time-like but doesn't actually close, but comes very, very, very close to being closed in such a way that if I would perturb the metric, it might close. Okay, and if I and so the point is, closed time-like curves we all agree are bad, but strong causality rules out curves like this, which are not closed but which are also bad-ish. I mean, maybe you might live with them in a given metric, but then as soon as you perturb the metric, they would start being closed and spoil everything. So the idea of strong causality is to rule that out. Okay. Okay. Now properties and one theorem, and then we are done. Okay. So I already showed you that so now we are back to globally hyperbolic. So everything I say from now on. So this is a kind of slight digression, which is how you can weaken global hyperbolicity and still have reasonable physics. But now we are back to globally hyperbolic, and let's state a few things. So first, I already said that this cannot contain a closed time-like path. That was obvious because every time-like path has to cross the Cauchy surface. If it does so, and if it's closed, it will cross it twice, and that's exactly what that will make it chronal and not achronal. Okay. Another one, which is very nice, is what happens if there are two Cauchy surfaces, sigma and sigma prime. Now, because sigma has the property that from any point here, a past inextendable curve must pass through this. So from here, if I start here and go this way, I must cross this. That's global hyperbolicity. But if I start from here and go that way, I must cross that. Right? Both are required. So this sort of sets up a family of curves which essentially along them you can travel from sigma to sigma prime, which means that which implies, and it's very intuitive, it can be made more precise, that sigma is topologically the same as sigma prime. So any Cauchy surface is topologically equivalent to any other. So for example, it cannot be that a manifold has a compact Cauchy surface and also a non-compact Cauchy surface, because these lines which are required to exist, if I translate one of these along the integral curves, I get the other. So if this was compact, that has to be compact, and if this is non-compact, that has to be non-compact. So that's one corollary. Okay, another one which is very nice. If you remember, we discussed J plus of P, and this plays a central role in singularity theorems. So this is the causal future. It's what can be accessed in the future of a point by time-like or null paths. And we never said anything about whether it's closed. Does it contain its limit points? And the theorem says that GHY implies J plus is closed. There is a proof of this which I will postpone a little bit. I'll give it to you very soon. The third one, which is almost a corollary of this one, is that the entire manifold, so an entire globally hyperbolic manifold M is topologically sigma cross R, where sigma is its Cauchy hypersurface, any of them, and R is basically the orthogonal direction, so it's time. So it's just this diagram, because there's always have to be these curves that causal curves that connect every sigma to every sigma prime pointwise. You can keep going forever in the future and past, and you get that topological correspondence. Doesn't mean at all that the metric factorizes into a space and a time metric, but topologically the whole space is sigma cross R. That's a nice thing to know. there's a nice consequence. Obviously, sigma cross a single point is a subset of sigma cross R, and you can identify this with sigma itself. Sigma cross a point is just sigma, and since 0 is a closed subset of R, this whole thing is a closed subset of sigma cross R, which is equal to M. So we've proved that every Cauchy hypersurface is closed. Again, contains all its limit points. So sometimes closed is built into the definition of Cauchy hypersurface, but this is the proof that it doesn't have to be in the definition. It's true by the very nature of Cauchy, which is this fact that all causal curves pass through, all inextendable curves pass through it. Very good. There are more details, and I have them in my notes, and there are more detailed, there's a detailed proof in Witten's article, but I, for lack of time, I'll skip that. Now, coming to a question that I think I was asked in one of the breaks. So this has to do with extending a space-time. So a GHY space-time M can sometimes be extended to a bigger space-time that contains M, which is also globally hyperbolic. Okay. So, and we can keep trying to do this. Supposing we are given a globally hyperbolic space-time, we can try to enlarge it by adding some natural set of points around it and make it larger while remaining globally hyperbolic. But our luck may run out at some point. There will be a point when we cannot extend it further, remaining globally hyperbolic. Okay. So this leads to a concept of maximally extended space-time. When there is no M double prime such that M double prime contains M prime and is globally hyperbolic. So as I said, you take your space-time, it's globally hyperbolic, you make it bigger, maybe it's still globally hyperbolic. At some point you can't make it any bigger. A nice example is this Garrosh example I already showed you of the fast light cone in Minkowski. And as we saw, if I insist that this should be a Cauchy hypersurface for some manifold, then that manifold is just the passed light cone. So the passed light cone is globally hyperbolic, with sigma being a possible Cauchy surface. Now I can extend this passed light cone by adding everything else. Sigma will no longer be a Cauchy hypersurface for that, but adding everything else, I just get back Minkowski space, which is certainly globally hyperbolic. Okay. Now if I decide to extend Minkowski space by adding bits and pieces here and there, it may be impossible, and probably is impossible, to have a globally hyperbolic space-time. And so Minkowski space is an example of a maximally extended space-time. So the idea here is you never want to restrict to a space-time that has the possibility to extend while remaining globally hyperbolic. So you always should extend it, and you stop only when you're convinced that it's maximally extended. This doesn't tell you how to find out if it is or not, but one of the motivations which I think everyone will be familiar with is that it might be that this is what you discover first due to a bad choice of your coordinates. Okay, and we know very well this happens with things like the exterior of a black hole and so on. You might think that your space-time has ended, when in reality there's a way to extend it remaining globally hyperbolic, and you should be looking for that. So it's like a moral principle that maximal extension is good, and you should look for that, and you should only stop when you're sure there isn't one.
Is there a classification of what those functions.
No, this I don't know if there is. There, yeah.
It's generally not a unique way of designing it.
A unique way, no, there need not be a unique way, I imagine. No. So there might be, M might have two different M primes that don't even, that only overlap on M and extend it in different ways. At least in the abstract definition, we don't require anything like that. We just say that when there is no possible way of extending it further, then it's maximally extended. Now you could get weird situations like I take M, then I extend it one way and then I'm blocked, but I extend it some other way and now I can go further or something. So that's okay. The end point of any set of extensions of a manifold is the maximally extended manifold. Asking that it's?
Einstein.
No. There could be many, absolutely. As I said, and I think I took this line from probably Walt, we assume this property to avoid artificially reducing the available manifold, for example, due to a bad choice of coordinates. Okay, now comes something that's really a little tougher than everything we've done so far, which is the study of the space of causal paths. So we take a point P, we take another point Q in the causal future of it, and we imagine all paths that go from P to Q, okay, but are causal. So we are not going to include this path, which clearly is space-like for the way I've drawn it. So they better be either time-like or null along their lengths. And now there's an interesting history. So a mathematician called Leray gave a series of lectures, I believe at IIS Princeton, and I think his notes, I could be wrong, but I think his notes date from 1953. And they are on hyperbolic spacetimes. And actually, it's easy to find a copy and download it. And he actually gave a definition, which is that a globally hyperbolic, so his definition of globally hyperbolic, so he was studying sort of Lorentzian geometry, so globally hyperbolic spacetime is one where CP, oh I call it CPQ, sorry, Q is written up, it's in the future of P, is compact. Now it's a little tricky to even understand this because it should be compact in the space of paths, which is not this, we need a topology on the space of paths before we can talk of a space of paths being compact. And I'll tell you in a minute what the topology is. It's not so hard. But you might ask, why did I give a different definition of globally hyperbolic than this? This is the first definition in the literature of global hyperbolicity. And the reason is that in 1960, what? I forget. Something. Gerosh showed that this definition, I'll call it the Leray definition, is equivalent to there exists a Cauchy surface, which is the definition I gave you this morning. And it's if and only if. So Gerosh actually started with this and said, I'm going to show you that if the space of paths is compact, between causal paths is compact, causal is very important. Then there exists a Cauchy hypersurface, and if there's a Cauchy hypersurface, then the space of causal paths is compact. Therefore, I can use existence of Cauchy hypersurface as an equivalent definition to this one. So, now we tend to think of this as the Garrosh definition of global hyperbolicity, existence of a Cauchy surface. That's the Leray definition, and there's a third one which is the Hawking-Ellis definition, which I'll just give you, and all of them, each of them implies the other two, so you can pick any one as you like. The only issue, and it's not very hard to show that every one implies every other, and I'll try to sketch it, but actually showing it would take the better part of an hour, and I think we should avoid doing it here. So let me give you the third definition, Hawking-Ellis. The causal diamond dpq, which if you remember was the causal future of P intersecting with the causal past of Q, is compact for every P and Q. Now there's one thing I slightly have hidden over here. This is a definition of global, all these are definitions of global hyperbolicity. There are three. But in order to make this definition sensible, you need to start by assuming something, and that something is the strong causality I showed you earlier. The fact that there's a region around every point through which causal curves don't pass more than once. That's important. And I believe, though I haven't personally checked it, that it's also required here. This one is so nice and intuitive that everything, including strong causality, is subsumed by having a Cauchy surface. I think everyone will agree that the last one is the easiest to imagine. It's just there's a initial value surface in the space-time. I think you can, if you go home and sleep over it and tomorrow morning you wake up, you'll still know that a Cauchy surface is an initial value surface, and if it's there, then the space-time is globally hyperbolic. It's very hard to understand intuitively what does it mean that the causal diamond is causal diamond is compact. Okay, it's not very easy. Compactness is not an easy thing to prove, and compactness of a space of paths is a devilish business. Now, in my notes, nevertheless, I very bravely have given you the proof. Well, I adapted the proof from references that this implies this one. I should take an opinion poll about how much you want me to discuss this, but I'll just say what it implies, what it involves, and I'll come back to this later. Let me just say what it involves. Sorry.
So
Yes.
when you talk about an initial microsurface,
Yes.
can you fill in for what? I mean, it's presumably for some sort of differential equation.
Sure, but
Characterize what differential
yeah. So, well, it's no, because that's not what it means here. A Cauchy surface is just one that every past inextendable causal curve has to pass through. So, I haven't actually, I haven't proved that a Cauchy surface is a good initial value surface because I haven't actually told you what problem we want an initial value surface for. And, if it's Einstein gravity, that's one thing. If it's some Born-Infeld action or higher derivative gravity, and, there's a morass of stuff there, as I'm sure, So the point is, it's more of a necessary condition, as long as your inextendable curves pass through your Cauchy hypersurface, you have a fighting chance to define an initial value problem because whatever it is you define will actually reach everywhere. Your domain of dependence is the full space. So at least you're confident that what you do will not sort of disappear or run down to an end before it reaches the rest of the space. It doesn't, so we call that an initial value surface in the sense that that's what we should start from to formulate the problem, but it doesn't mean we have formulated the problem.
Are you going to talk about, I mean, there are also things when you have non-locally hyperbolic space.
Of course.
The Cauchy horizons and so
Yes,
forth.
yes.
There's another phenomenon there which things tend to go wrong. topologies that develop singularity.
That's, yeah.
Maybe in the original quiet spacetime, but
Yes.
as soon as you rattle, the fluctuations build up singularities. Again, it's the same question about.
Well, some of this, for Einstein's gravity, some of this is encoded in Hawking's and Penrose's singularity theorems, which I will be addressing. I mean, famously, Penrose's singularity theorem is based on the existence of a closed trapped surface, which is something which after that, once it forms, if you rattle it, it's too late, you're still going to reach a singularity. We'll come to all that. So this is really setting the stage. I mean, this is what GR is like. There's a lot of setting the stage before you actually do things. So just let me say briefly what it entails to show that CPQ is compact. So first of all, compact in a topological space means every open cover admits a finite subcover. So if I have a collection of open sets that cover my space, the space which I'm trying to check for compactness, anytime I can cover it with open sets, there's a subset of that cover. It's not that there exists a finite subcover, but the cover I give you, from it I should be able to pick a finite set of open sets which also cover the space. Now, as you can see right away, this is a horrendous thing. Nobody is actually going to take a space and list all possible open covers and see if they all have finite subcovers. In reality, people use the Heine-Borel theorem, theorem in basic calculus, which says that if, so that compact, so for a metric space, compact is equal to closed and bounded. Maybe this isn't the Heine-Borel theorem, that's for maybe for just ordinary space and for like real line or real or Euclidean space. But the more general theorem is that compact is same as closed and bounded, and this is what physicists know. We know what closed is, contains all endpoints, and bounded things, nothing goes to infinity in the given metric. So this is easy to check. So this isn't the thing you can check, this is the thing you can check. However, in the space of curves, it's not a metric space, because what is this space? It's the space of all curves like this, and we'll define a topology on it, which I'll tell you in a second, but it's certainly not going to be a metric topology. It's an infinite dimensional space. We're not going to find any metric on it. So this doesn't work either. So closed and bounded is not what you can check. So you have to step back, and what you have to actually do, and this is in Wald's book, is that compact is equivalent to sequentially compact. And sequentially compact is much more fun. It says basically that if I have a sequence of curves, then they should converge to a limiting curve. So sequentially compact means that the sequence, so let me give you the actual definition. It's in an appendix. So every infinite sequence has a subsequence that converges. Okay, it's actually much more complicated than that. Sequentially compact for points is every infinite sequence of points has a subsequence that converges to a point. Okay, for curves, it's actually more complicated. There's a whole discussion on convergence curves, and it needs time to define. And then you want to show that every sequence of curves converges to a convergence curve. And this is something that you can show starting from the Cauchy hypersurface definition, and this is what makes these two equivalent. The reason why I brought up Leray et al. Is not for historical reasons, but we are going to use this. The space of causal curves between 2 points P and Q is compact, which means that every infinite sequence of causal curves between P and Q converges to a limit curve. Yes.
So how do you define distance between different parts?
Yeah, we don't. Yeah. Yeah. So we don't do convergence in the sense of metric space. We just do convergence by defining open sets. So that's the whole point. It's not a metric space, right? Because if it was a metric space, it would be infinite dimensional, because a curve needs infinite amount of data to specify it.
Space with some
Yeah. 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 Yeah.
That's fine.
Okay.
You can speak about limit points with respect to one.
That might be possible, yes. Yes. But that's at least, yeah, that might be possible, but that's.
My question
Yeah.
actually was that you have different characterizations.
Yes, of course.
And somehow it's a question how to take the difference between which points.
Absolutely. Yes, yes, yes. And exactly, and that's why the proof, which you'll find in Wald's book, and also Witten gives a very nice, slightly more intuitive sketch, is that first you define sequentially compact for points, then you define a convergence point by this definition, then you ask for curves that pass through that point. So for every point in a sequence, you ask for a curve that passes through it, and then the convergence curve should pass through the limit point of those points. So it's a multi-step process. So actually, I'm not going to go through this thing. I think the only thing I should tell you is what is the topology on this space of curves. And the topology on the space of curves is that, so so of course I have a topology on the manifold. So that means I have open sets. Now to define a topology on the space of curves, I will just tell you. Sorry, I just lost it. I just want to make sure I don't miss something in the definition. I think I gave this earlier. Yeah, here's the topology in terms of M. So this is M, this is P and Q, these are fixed. So let me take an open set U that contains both P and Q. This is an open set of M. So this is an open set of M in the usual sense. Now I'm going to use this indirectly to define a topology on the space of paths, and that is defined by saying that the set of all O of U is the set of all causal paths fully contained in U. So as you can see here, given a U, an open set will be O of U will be the set of all causal paths between P and Q, which however do not stray away from here. I mean, there could be a causal path which goes out of U and comes back. That's not in my open set. Okay. So once I've defined this open set, then I can actually talk about whether every infinite sequence has a subsequence that converges, and that will tell me that CPQ is compact in that topology. Now I sense partly from your reactions, that this is getting horrendously abstract, and it is. I mean, it's really, this is like the hardest part of the subject in a sense. But I'll just make a few comments which might help you. One is that this compactness property, this theorem, that this follows from Cauchy hypersurface, is not true if we weren't talking of the space of causal paths. It's very easy to look at space-like paths which don't have this property. That is, space-like paths which never converge to a limit. I can make a family of space-like paths that simply don't converge to a limit path, and Witten gives a very nice example. And basically, you can make your path do weird stuff like that. That's definitely not causal. And you can have a family where this looks like a sine curve, can be something like sine pi n t, and so or sine pi n x, I guess. What is the example? Sine x equals sine pi n t. That's this. And is this x equals sine pi n t, or this is t equals sine pi n x? Maybe I've written it wrong. Anyway, you get the idea. The point is that as n increases, my path just becomes more and more jagged, but it's not converging to any paths, right? The more jagged path between one end and the other doesn't have any limit. There isn't a limiting path. And the problem with paths like this is that they are not causal. Once a path is causal, it's constrained to behave much better. For example, it cannot do that stuff because all that stuff is making it go space-like somewhere. You just cannot do that. It's forbidden to do that. And that's the whole beauty of causal curves. A causal curve can bend, but then it's, oops, this tangent is tending to 45 degrees, no more bending beyond that, and it has to keep climbing upwards because we're going up in time, and it can bend the other way, and there's not that much it can do. It just has to bend between two 45-degree angles. Okay, a space-like curve, on the other hand, can just do a lot of stuff. So that's the reason why this theorem only applies to CPQ, which is defined as the space of causal curves between 2 points. Okay, and I think now we are really done with this. The last definition I'm going to skip, and I'll come back to it if needed. The statement that the causal diamond is compact, which Hawking and Ellis use as a definition of global hyperbolicity. Actually, it goes through this. So, in some sense, you use Cauchy surface to prove this, and you use this to prove that dpq is compact. So, in summary, GHY is Cauchy surface, CPQ compact, where it's the space of causal paths, and then causal diamond compact. So we'll use any of these at will. And that, I think, completes the discussion of Lorentzian differential geometry, and I'm sure you'll agree with me that this subject doesn't feel very much like ordinary differential geometry. You can take a full course in differential geometry without dealing with any of these sorts of, or most of these sorts of questions. One last theorem, which actually comes from this property, and which is pretty important, as you can imagine. In a globally hyperbolic, so this is the theorem. In a globally hyperbolic spacetime, there is and 2 point and okay, there is a unique geodesic of maximum proper time. So here we are in the, remember that in this subject, CPQ is always with Q in the causal future of P. So geodesics that go from P to Q will be causal geodesics. So they have to be time-like or null. There's a unique geodesic of maximum proper time between P and Q. So earlier we had this concept of convex neighborhood, normal neighborhood, where there was a unique geodesic between 2 points. But now in the entire space-time, there's a unique geodesic as long as we maximize the proper time. So there can be other geodesics which take less proper time, but the highest proper time comes from. So there's one with highest proper time, and that exists. Again, maybe we can, we can see obvious statements like if I had a geodesic that was space-like, then of course it could just, what could I do? I could, well, maybe I shouldn't go into that thing. Okay, let's stick to time-like geodesics. One thing you can see is that minimizing the proper time is very easy. So there's a famous construction. If I want to go from here to here, you might think that that's minimizing something. Actually, that line in space-time is maximizing the proper time between here and here in Minkowski. And how do I minimize it? Well, I simply make a jagged curve whose every segment is null. And I can always reach there from there by a jagged curve whose every segment is null, but a null segment has 0 proper time, so the whole thing has 0 proper time. So I certainly minimizing proper time is, there's no point, because you can minimize it all the way to 0 and you learn nothing. However, maximizing it is a thing, and there's a unique such geodesic. Okay, we now have all the preparation to talk about focal points, and this is the last part. So we'll break in 10 minutes, and then maybe after that another half an hour, 40 minutes should be enough to at least cover the Raychaudhuri equations. Any questions?
Maybe a small question about this topology. So open sets intersect, and it's a given open set in the features of groups, but also the union.
Yes. Yes.
You take the union of two sets and pick up 2 points which from different
Yes.
sets.
Yes.
So it's not obvious that all the passes.
No, I think, okay, let's try. So I have O1 of U1 and I have O2 of U2. Now you want to look at intersection. So since, oh, in union, okay, union. So U1 and U2 are open sets of the manifold. So they are ordinary open sets, and U1 intersection U2 is also an open set. Oh, sorry, union U2 is also an open set by the existence of a topology on the manifold. Okay. Now O1 of U1 is the set of all causal curves fully in U1, and O2 of U2 is the set of all causal curves fully in U2. So is it true that O1, sorry, actually I shouldn't put a 1 or 2 here, O of U1 and O of U2, that's the label. So O of U1 union U2, I think your question is this equal to O of U1 union O of U2? And I think that's...
Maybe there is some pass, this causal pass, which doesn't belong to this. Especially if one point from U1, which don't belong to U2, and another point from U2, which don't belong.
Yeah, I see that. That's a very interesting thing. So you're saying if I have a U1 and a U2, then I might have a path, and this is whole thing is U1 union U2. So, and here is P, and let's say here is Q, and I might have a path sort of like that. So this path is, well, no, the problem is that P and Q should be, I think, this only makes sense if P and Q. So since these open sets depend on P and Q, I think every open set has to contain both P and Q. to apply this definition. So P and Q are here. So now of course I could have a path like this, but this path is in O2, and if I have a path like this, then it's in O1. I think P and Q have to be inside all and therefore in the intersection of all, because we are defining this topology after fixing P and Q. Yeah, we can discuss it. Yeah.
You can take like categories, P Q, and you have two tests you want to choose, so there is no path at all. What's the reason behind the
No, so the topology is defined by saying first fix P and Q and then consider all open sets of M that contain both P and Q. Okay, and now O of U will be the set of all causal paths fully contained in its corresponding U. So first you have to fix P and Q. Now,
so you want like
U1 contains P and Q, U2 also contains P and Q. I think the contradiction that he was suggesting could arise only if P could be here and Q could be there. But P and Q have to be in U1 and also in U2 and therefore in the intersection.
Yeah, I'm just thinking you want, so you don't have a path from P to Q, you are. You don't have a path from P to Q in U2, but you have a path from P to Q in union of U1 and U2. You just
Okay.
pieces.
Okay, I see. Okay. Yeah, I don't know how that would happen, but maybe we can look. Huh? Yeah, sure, please.
So, say this is U1.
No, U1 has to include both P and Q.
Yeah, so U1 is.
Oh, both of them. Okay, it's disconnected. Okay.
U is
yeah.
maybe smaller. And you have coming here. So if you take the union, it looks something like this. And you have a path here, but you don't have path here or here.
If you take both U1 and U2 to be disconnected, and you manage to take I see, and then you take a union which is connected. Yeah. No, so in his example, I think this this is empty. So there are no paths in this open set O, because it contains all the paths that are fully contained in U, but there are no such paths. So he's saying O of U1 is empty, O of U2 is empty, but O of U1 union U2 may not be empty. That is an interesting example. But let's see the fine print in the theorem. Not now though. Okay. Good. Okay. So the rest of today's discussion will be about geodesics. I've already said a lot about them. I just need to say one more thing about them. So I told you that they're described by a tangent vector dx mu by d lambda. One thing I forgot to say in the morning is that if they're time-like, then g mu nu t mu t nu is less than 0. And so I can actually choose a normalization where it's just -1. This is the usual thing, that any 4 velocity u mu can be normalized. U with u dot u is -1. So I can pick that for the time-like case. And the nice thing is that if I differentiate this relation, I get 0 by the definition of geodesic, because I get t dot d lambda of t, and therefore this doesn't change. So this norm, whatever I chose to be -1, will be -1 everywhere. If it's -1, it can't change to 0 or +1 because it's constant, and therefore a time-like geodesic is actually, so we proved something we didn't know before, is time-like everywhere. It can't have a null segment, or there can't be a geodesic which is partly time-like and partly null, or partly time-like and partly space-like. None of that is allowed. Because once I normalize it to -1, that tells me it's time-like, and that's a fixed property which is maintained along the geodesic, and so it just has to be always time-like. Okay. The same is true for null. If it's null somewhere, then it's null everywhere, as long as it's a geodesic. So I can replace this by time-like. I can just say null geodesic. So in this case, as you know, G mu nu T mu T nu is 0. It's still true that this is 0 everywhere. That means if it's chosen to be 0 in some segment, then it will continue to be 0 forever. And therefore, null geodesic is always null. So this is something rather simplifying. There's obvious looking statements, but we can focus on time-like geodesics, we can focus on null geodesics. We never have to focus on geodesics which are a bit of both. So from now we'll be studying them separately for the time-like ones and the null ones. We could also invest effort in studying space-like ones, but it's no fun and doesn't do anything for us, so we won't study those at all. Okay. Now a nice result is the theorem is a definition actually. If two or more geodesics. So I'm not going to say causal, but they will be either null or time-like. And when they are specifically one or the other, I'll say so. If one or more geodesics from P meet again at Q, then notation. Some people think of the geodesics as starting at P and ending at Q, then we say that Q is a focal point. But another way of saying it, which is also very common, is that P and Q are conjugate points. Okay. So let's look at examples. First of all, we can do this, we can step back from space-time and do this in ordinary space. Okay, it's still possible to talk about focal points. You might have two or more geodesics that start from one point and meet again, and then you would again have a focal point or conjugate points. And the most beloved example is a two-sphere, or indeed any sphere. So of course, starting from P, we have all the longitude or great circles going down, which are all geodesics. They get out from P in all directions. And it's pretty obvious. You start from P, you pick a direction in the first place from this tangent plane, and then you just follow it. And you'll obviously be on a great circle. And everything will be fine until you reach here, where all of them meet. So geodesics starting from any point have a focal point at the diametrically opposite point of the sphere. Okay. So P and Q are conjugate points. Any pair of points diametrically opposite on a sphere are conjugate. Now a very fun thing is that a conjugate point is a point where something is going wrong. And this is easily described like this. Imagine I travel from here. This is P. And all along my travel, I'm confident that I've taken the shortest route to get where I'm going. This is the shortest route to get from here to here. And I reach here and I'm very happy with my progress. And all along, I've just been traveling parallel to my tangent vector and not thinking about the global picture. And I keep going past this point. And I reach here. So this is Q, I reach a point Q prime. Now, any of us staring at this would point out that this is no longer a geodesic. Okay, it's not extremal and it's definitely not, it's not minimal for sure, and it's not even extremal. You can actually continuously shrink this path by simply taking it over the surface of the sphere until it turns into this, which is the actual geodesic from P to Q prime. Okay, now where did things start to go wrong? They went wrong exactly at Q. Until Q, everything was fine. We were nice and geodesic. We were minimal. We were absolutely economizing our distance. And as soon as we crossed Q, things began to go haywire and we are no longer on a geodesic. And the diagnostic is that this is exactly where new geodesics started to meet. So we see that in this example, past a focal point, a geodesic is no longer geodesic.
I don't see why it's not geodesic, but because you have to satisfy the geodesic equation.
Yes.
Not maximum or then
Yeah, well, it should be stationary to be a geodesic, and it's not even stationary because this curve has a continuous deformation. Imagine a piece of string doing that, and I simply continuously move this along this, and it shrinks, right? This rubber band from here to here shrinks. So, in fact, any infinitesimal deformation of this way or that way will shrink it. So, in any small interval, it's a geodesic. I agree, but on the whole, it's not. It's supposed to extremize the length, and it's not doing that.
But it is so hard to use it in the sense of stable. Like if you define the ability as like growth, you might actually.
Well, if even an infinitesimal deformation changes the length, right? So it doesn't seem like it's even minimizing. Maybe it's a saddle. Okay, okay, fine. But in any case, in this example, I haven't proved any general theorem. It's just an example. So let's see what happens in more generality. And for that, let's keep our point P here and our point Q here and a point Q prime here. And let's say the idea is to get to the net destination at Q prime via a geodesic. And we have a geodesic from P to Q as we have in that figure. But this is now in a general Riemannian manifold. I still haven't gone to Lorentzian. And let's say I have a focal point, but this time I do something a little different. I assume that two infinitesimally nearby geodesics are converging here. Okay. The reason I do that again is to rule out topology causing there to be some geodesic which goes somewhere else and comes back here, which I would not be able to make statements about. So I'm assuming that I have two infinitesimally close geodesics. Okay. Now supposing I was on this one as in that example and I blissfully continued to Q, I can now show you that there must be a shorter path to Q prime from P. And how do we see that? So there are two steps. It's very nicely explained in Witten's notes. It's actually, this argument is due to Penrose. He called it a crude argument, but now it's gone in the literature as the default argument. It's involved, it's in Witten's review. And the idea, so I've just given it some names. One is switching and the other is smoothing. So the switching and smoothing prescription will lead to a shorter path from P to Q. So the first thing is, instead of going P to Q prime along this line, I have colored chalk. I'll go from P to Q along this line and then continue that way. This is the switching step. So I reach Q and I discover there's another geodesic that also reached Q. So, and it's infinitesimally close. So I just switch to it. Okay, I can't change the distance because this distance by definition is the same as that one. So the total distance hasn't changed by switching. But now the new path, the orange one, has a kink. There's a kink over here because it's pretty clear that if I switch from this curve which was smooth to this curve and then continue on this one, then it's not smooth at that point. I've introduced a deficit angle. So once I have a deficit angle, it's pretty obvious to the eye that I could just skip past it in a local region by just leaving this direction and jumping from here to here, making it more smooth. You can see visually that this curve, the red one, looks like having a better chance than the orange one to be a geodesic. It's literally shorter.
Sorry, but why can't two geodesics be tangent at focal point?
Tangent at a focal point. No, I don't think they can be tangent at a focal point. Why not? I think I can prove this, but I'm not sure if I can do it just now. There might be some exceptional case where that's true, but I think in general that's not the case. I think that no, I think the statement is general. So okay, let's check. We can discuss this point also later. Okay, so the claim is that when you have two geodesics that meet at a focal point and you want to proceed to a point beyond that, then you can first switch from your original one to the other one that met it at the focal point, and now you develop a kink and now you smooth the kink, and the more you smooth it, the more you're going to minimize the distance. But we are not going to go to the extreme of finding the new geodesic. We just want to prove that the orange curve is not a geodesic. And if that's true, then the white curve is also not a geodesic because it has the same length as the orange curve. And that proof is actually just the fact that by smoothing this over the kink, you're actually shortening the distance. This is the key idea. So this is Penrose's idea to show that beyond a focal point, the distance is no longer minimized. Okay. Good. Now there's an analogous result which is going to be used actually, but we'll continue in Euclidean. Supposing my geodesic is not from a point P to another given point Q, but instead I have some submanifold S, and my task is to land on S in the shortest distance possible. I don't care where I land. Okay, and it's very easy to see that I will land orthogonally, because if I don't land orthogonally, then I can wiggle it and shorten my distance. Okay, and this same argument says that if I start from here and I have a geodesic that focuses with this, then I can shorten my distance by simply smoothing out over this kink, not necessarily landing at that point, just landing on S, because my goal is to land from P on S in the shortest possible distance. Doesn't have to be at the point. There's no point Q in this diagram. So this is a generalization of this. Is it clear what the generalization is? It's just, yeah, it's exactly the same. So, sorry, I think I drew this wrong. So, actually, yeah, I've written this in my notes, excuse me. In discussing manifolds, yeah, sorry. So this is P. It hits the surface Q orthogonally somewhere. Now, supposing from some point P prime, sorry, I drew it wrong earlier, it hits the manifold orthogonally somewhere else, and this is also a neighboring geodesic. That's the argument. Okay, this is what I wanted to draw. So this is a different point q prime on S, but the distance between p prime and q and between p prime and q prime is the same. So both of these are geodesics to the subspace S, both intersect orthogonally and both take off from the point p prime. So this is an illustration again of focusing, but this time if you look at it starting from there, the geodesics taking off from S are focusing here. And now by the same argument, all I have to do is smooth out this kink. So I take this as my starting geodesic. I notice that this has the same length, so I switch to this one and then I smooth over the kink and I find that this is shorter than the original one. And so there is again the focal point indicates the existence of a geodesic of shorter distance. Yes.
Actually, it seems a little bit strange. Why, given a focal point like this,
Yes.
or an intermediate point,
Yes.
why do we actually need to prove that it is not a geodesic if we pass through this focal point? Why are we following this procedure? This is
Because
conceptually it doesn't, you have you want to go from point A to point B and you want to find the geodesic. Why do we need really to investigate whether the path between these 2 points is going to be geodesic if we also add the intermediate point? It's by default it would tell me that it wouldn't be geodesic.
No, why by default? Why would it tell you that by default?
Why would that be then?
Okay, I can give you, I'll tell you two things.
Exactly what you also saw, and it's not there.
Yeah, it's not, of course, but we had to show it. In fact, there are more rigorous proofs. I don't know why you're saying it's obvious. It's this, as far as I can see, this is a proof that there's a shorter path. It could have been that these two meet and then, well, these two focus, but still this is the shortest path. We have to realize that we are now, after this meets here, we are claiming that a path with a kink is a geodesic, and that can never be so. That's what the second part of the argument says. A geodesic cannot have a kink, end of discussion. So I mean, they are trivial observations, but when you combine them, you learn something. Now, why are we using this is because we'll find a diagnostic which is called the Raychaudhuri equation, which tells us the conditions under which focal points exist. And if we combine this with other conditions, which are global hyperbolicity, which I spent all the morning trying to develop, then we may find situations where actually all geodesics coming from S will focus by some distance or some time actually, because we have to move this discussion to space-time, and we'll conclude that the space-time itself is geodesically incomplete, and that's Hawking's singularity theorem. So the existence of focal points for all geodesics, if we can argue that all geodesics must have focused by some time in the past, then before that time in the past there can't be any geodesic, and it basically contradicts global hyperbolicity, and we'll conclude that the space-time is either singular or geodesically incomplete, whichever words you want to use. So that we'll do. Right now I've only done all this for spatial geodesics, and there's nothing much to discuss in this in the Minkowski signature, Lorentzian-signature case. The only thing that changes is that we'll restrict to geodesics that are time-like, and we're not going to discuss null right now. Null will be on Monday. It's actually a very different discussion because of the fact that lengths don't make any sense, because the length along a null geodesic is 0 whatever you do. So let's start with our original diagram. So here's P, here's the focal point P prime, and here's the point, so here's P going to Q with a focal point P prime, and here's another geodesic that meets. Now assume these are time-like, and that makes this figure very ugly, so let's try to draw it to look time-like. Let's put Q here, and let's put P prime here. Now at least everything looks time-like, so all these curves are time-like. But we found that these geodesics have a focal point here, and they're infinitesimally close by. This time what happens is that when I smooth like that, I actually increase the proper time. I'm not decreasing it, But in fact, with time like geodesics, we want to maximize the proper time, not minimize it. Okay, I probably have given this argument before, but it's easy to show that minimizing the proper time just leads to zero proper time. You can always zigzag and reach anywhere you like in zero proper time. So that's not a great achievement. Maximizing is a well-defined process, and this switching from this to this and then smoothing that part makes it increases the proper time between P and Q. Okay, and it's easy to see that this line, which is almost vertical, will have the longer length invariant proper time than this and this, which both are much closer to being null. So they'll be much shorter in the invariant distance sense. Okay, so with Lorentzian signature, focal point implies can increase proper time. Okay, and this construction will also work in Lorentzian signature. I hope it doesn't need to be said again. I simply turn this sideways, let these things go vertical, and I have, let's say, a manifold which might have been my Cauchy hypersurface. I have two time-like geodesics which focus, and then beyond that, neither of them will maximize the proper time, and by smoothing, I can show that there's a longer proper time. Okay. Try to imagine how this might play out in the null case, and it's very entertaining because everything is zero in all the steps. Okay, so that will come. Okay, is this the break time for a break? Yes. Okay. Good. Okay. Well, thank you all for still being here. I'm amazed. So now I will talk about the Raychaudhuri equation, and I think we can do this in half an hour, and then we'll conclude for today. So Amal Raychaudhuri was quite a legendary figure in Indian science and in the relatively recent history of Indian science. Was a young researcher in Calcutta, and when he wrote a paper in 1955 on the equation that became known as the Raychaudhuri equation. And it's sort of a fun story for us who work in India because he was employed as some kind of scientist reporting to a senior who wanted him to work on solid state physics and in particular on the properties of metals, and he was obliged to churn out two papers on metals which had exactly zero impact on physics. I think one of them has one citation and that's it. And he was told that general relativity was obviously not of interest to anyone. But he loved it, and he went on to write a paper that's strikingly simple but somehow sparked off a seminal kind of train of thought that was developed later by Penrose and by Hawking. Now it turned out that he published this in Physical Review in 1955, and Komar, apparently not knowing about this, published a similar result in 1956, and both had sort of very similar motivations, and but neither of them actually succeeded in what they set out to do. They came out with a nice equation, but their motivation was something that they didn't have the technology to reach. And an important reason for that is that this was 2 years after Lerais' definition of globally hyperbolic manifolds. But Lerais' work was very obscure. It was given as a series of mathematics lectures in Princeton, not published. It's just some lecture notes. And it became, the concept of global hyperbolicity we've been discussing became clear to everyone around mid-60s due to Penrose and Hawking's work. And then that's around when Garrosh did his work and gave a simpler definition, and then everything became much clearer. Well, in the 50s, they had no access to any of that. So they didn't even try to specify what sort of space-time they're working in. But the idea was the following. There were various solutions of Einstein's gravity and various studies due to, I guess, Lemaitre, Bondi, Eddington, uh, Robertson, and so on. But particularly the FRW type of metric. Well, it has a scale factor. And of course, if you solve Einstein's equations, the scale factor, depending on the initial condition, is either going to go to 0 in the future or in the past. So, and this is sort of what led to the idea that there could be a Big Bang, particularly because its initial condition was such that it was really going to go to 0 in the past. The universe is expanding. It's very intuitive. You don't even have to know GR to imagine that if the universe is expanding in the future, then it must be contracting to the past, and at some point it should just bang into itself and there should be a singularity. The problem with this metric is that it's homogeneous and isotropic. So it doesn't depend on any angles in space, and it doesn't depend on the position in space. So that position, so this being independent of x is homogeneous, and this being dx dot dx is isotropic. Okay. So, well, we had an idea that there seems to be a past singularity, and I think the term Big Bang was sort of coined around that time. But the problem was that it's only shown if you have something that's homogeneous and isotropic, and obviously there might be broad reasons to assume the universe is homogeneous and isotropic, but locally it isn't. Otherwise there wouldn't be a Royal Institution or anything. There would just be an isotropic and homogeneous universe. So obviously you're interested to know how generic the universe can be, and yet have this Big Bang-like behavior in the past. So the burning question was, what if there is no symmetry assumption? Is there a Big Bang if there is no symmetry assumption? Can you show it in general? Now, Raychaudhuri states as much. I think Kumar also states as much in the introduction to their papers, which I think are both very short. Strangely, many years later, a decade later, Hawking, although very approvingly cites Raychaudhuri's work, accuses him also of using symmetries. And the point is, as I'll explain, that Raychaudhuri used some symmetric energy momentum tensor, but only after having derived an important equation, which is the equation named after him. And so you can take his paper and not use his energy momentum tensor, and then he has a result which is general, doesn't assume any symmetry, and it's that result which can be cycled again and again to understand the behavior of universes in the absence of symmetry. So this is just a kind of overview. Let me actually get to it. So the first thing that's relevant here is a congruence of geodesics. This term used to scare me for years because it seemed like something very esoteric, but it's nothing but so space-time M and an open set O. Then it's a family of curves such that every point P in a given open set lies on precisely one such curve. You can see that this Cauchy hypersurface-like idea is sort of coming in, but it's not there because we haven't said that there are manifolds where everywhere this happens. We just look at a local region where there's a family of curves, and we ask what happens in that local region. Now there's a beautiful set of arguments which tell us that we can go to a special coordinate system called synchronous coordinates in at least in a finite neighborhood of wherever we might be, in which the general metric is replaced by minus dt squared plus a spatial metric, which however depends on x and t, dxi dxj. And this amounts to making certain coordinate choices which are quite natural. So first, algebraically you can say this amounts to g00 equals 1 or equals minus 1 and g0i equals 0. And since these are d conditions, so in d dimensions where I have d changes of coordinates, I should be able to do this. Of course, it could fail far away from somewhere, but in some finite local region, I should always be able to do this. Now, Raychaudhuri actually gave a nice picture of how to do this. He said, let me take an initial space-like surface. Again, he probably meant for it to be Cauchy, but he didn't give the conditions. So, for example, we didn't argue that its domain of dependence is the whole manifold. Just start with some initial surface. And let's draw an orthogonal congruence. So, I'm specializing. He considered the non-orthogonal case also. Let's pick a point here. And let's take one geodesic. And okay, now let's work with only time-like. So Raychaudhuri only worked with time-like geodesics, and the entire subject of null geodesics in the same context came later with the work of Sachs, the same Sachs who is the S of BMS. And it's a different subject with its own separate complications. So right now, everything that Raychaudhuri and I believe also Komar said is true for time-like. Raychaudhuri actually in interviews in latter years, of course he's no more now, but he said, you know, people give me a lot of credit for my equations, but the real equations were some that people needed were the null ones, which I didn't develop, so I don't know why they credit me. In fact, they call those the null Raychaudhuri equations, which is a little bit too generous because they were found by Sachs and they were nowhere in Raychaudhuri's work. But okay, that's a subject for much later lecture. So right now we have time-like geodesics. Now, as I told you, we can have an affine parameterization where the proper time is my parameter along each geodesic. So let's imagine that this is defined to be the origin of my coordinate system. So t and x is 0 and 0. And now what I do is I follow the geodesic, and at every point I assign a time t, which is the proper time between here and there. Okay, so t is the proper time starting from my initial surface sigma along the geodesic that happens to pass through it. Since this is a congruence, there's always one geodesic, I just follow it. If I follow it forward, I get t. If I follow it backward, I get some negative time. Okay. Meanwhile, this is a d minus 1 dimensional spatial manifold. Okay. So on this, I just choose some spatial metric gij of x. I do it once at t equals 0. Okay. This, of course, I can do. This is ordinary Riemannian geometry. I just take a 3 manifold and I give it a Riemannian metric. This is not space-time physics, so I can do it. Now, if I'm, say, here in this manifold at a coordinate x, I simply go up, and at this point, I assign the time to be the proper time along this, and the value of x at this point to be the same as the x at this point. I simply continue x along the geodesics. So my coordinates are fixed once and for all on sigma, but since I can go to any other copy of sigma along a time-like geodesic, I'll give the points, all the points on one geodesic, I'll call them the same spatial point x. And only the time will vary and the time will be the proper time. Is this construction clear? So to say it again, if I pick this point, how do I find its coordinate t and x? Well, I first check what geodesic it lies on and I draw it. I have a congruence. and every point lies on one congruence, on one geodesic of the congruence. So I follow it down till it hits sigma. I measure the proper time, that's t, fixed. Then when I land on sigma, I ask what is the coordinate value of this point on sigma, where I've chosen a coordinate system and written a metric. That gives me its point x. Done. And it's very easy to see that with this you get synchronous coordinates. You get these coordinates. Okay, G00 is -1 precisely because my time is the proper time. G0I is 0 precisely because these intersect this orthogonally. So everything is easy in synchronous coordinates. Okay, good. Okay. Now, for the first time, at least in my lectures, we ask about the Riemann curvature. We are not using Einstein's equations, we are just using its definition. So you all know the definition of Riemann curvature. It has 4 indices. I can take a trace on 2 and I get the Ricci curvature, and I'm going to take the 0, 0. I have a fixed coordinate system, so 0, 0 is meaningful. In my coordinate system, the time component. And obviously this is a bunch of terms just from the definition of Riemann tensor in terms of Christoffel symbols. Good. Now, it's actually the case that in synchronous coordinates, gamma mu 0, 0 is 0. Just from these two conditions. It's very easy to show that this component of the Christoffel symbol vanishes. Right? You can expand it out, you can take mu to be time or space, and you'll see that it depends on these things. And by the way, these are true for all time. Okay, and it's easy to show that they can be implemented for all time. So with that choice, this term is dead and this term is dead because both of them have gamma alpha 0, 0. So there are only 2 terms left. Okay, so that's a simplification. Now we work out the only thing that we need is gamma alpha 0 alpha or gamma beta 0 alpha. So 2 arbitrary indices here and 1 0. And we easily find that gamma alpha 0 beta is equal to a half G alpha gamma G dot beta gamma. So everything simplifies in synchronous coordinates is the moral of this story. And eventually this implies that gamma, so I don't expect you, if you're new to this subject, relatively new to this subject, to follow every equation, but they're all easily derived from the previous one. And we find gamma 0, 0 beta is 0. We already have gamma mu 0, 0 equals 0. So if there are 2 zeros in gamma, it just vanishes. And there's the only one that's really, therefore, at least 2 have to be non-zero, and the one that we need is gamma I0j, which there's also a gamma ijk, but that's not very interesting. That just comes from the Riemannian geometry of the initial surface, so it's something, whatever it is. But gamma I0j turns out to be a half gik g dot jk. Now, whenever you see an inverse metric, you should ask if it's the inverse in the 3D sense or the 4D sense, because these are 3D coordinates or d minus 1 dimensional coordinates. But fortunately, again, in synchronous coordinates, it's the same thing because there's no cross term and this is 1. So the inverse of the 3D metric and 4D metric are the same. Okay? So this is an important result. And now we can plug that back into this, and we find the following equations. So we are not writing Einstein's equations. I want to emphasize We're just manipulating the definition of the Riemann, or actually the Ricci tensor. And we'll see what that teaches us. So R00, which I started out trying to calculate, is minus half del 0 of Gik G dot Jk, sorry, G dot Ik again. Everything has to be contracted on the right side, minus 1/4 Gik G dot Jk Gjl G dot Il. It's slightly tedious, but it's not no more than plugging in these results that I've given you here into these two terms. So that's R00. Now comes the insightful idea that we should give names to these quantities and assign a physical significance to them. So the first thing we should do is to talk about the determinant of the spatial metric, det of Gij, which, as I've shown you in these coordinates, is the same as the det of the four metric. So I don't even have to say Gij. Let's take det of G to the half. Okay, why is this an interesting quantity? Well, when we integrate on a space-time manifold or a spatial manifold, this is always in the measure. So it sort of measures the scale of distances, and it's going to vary as a function of x and t. Now, the goal here is to diagnose whether geodesics have a focal point. So here's my surface, and I want to know whether two outgoing neighboring geodesics have or don't have a focal point, and if they do have, then where. Alternatively, if two backward propagating geodesics have a focal point, and if so, where, under what conditions. That's the goal. So here we are, in fact, in the situation I discussed earlier, where we are talking of geodesics from different points of a manifold and asking whether they focus at a point. Okay. Now, if they do focus, then at this point or near this point, we need to have det G equals 0, because det G is a measure of the separation scale. And as I propagate up, if det G is tending to 0, then these geodesics are getting closer and they're going to collide when det G goes to 0. So this is the diagnostic for a focal point. Good. So now we define, we can give some names. So, oh, I rubbed out a very useful equation. Sorry, I'll have to write it again. Define theta of x, everything depends on x and t. It's equal to half Gik G dot Ik, but by a simple theorem in matrices, this is also equal to half det G inverse det G dot. So theta is the quantity, it's like a logarithmic derivative of G with a half in front, and it's going to tell me how the det G is growing or decreasing with time. And then I'll be able to trace whether it ends up somewhere where it decreases all the way to 0. And that's going to be my focal point. I want to emphasize this is an analysis of focal points, and in modern language, it's no longer to be thought of as an analysis of singularities, although both Raychaudhuri and Kumar probably thought they were analyzing singularities, and they couch their discussion in that language. It's not clear from the analysis whether anything we find will be a problem with these coordinates, which we now call a coordinate singularity, or it will be a real singularity. So we are just going to pursue this and see where it takes us. Okay. So theta is a crucial quantity that we are going to call the expansion or geodesic expansion, to give it its full name. And I think it's pretty clear from its definition why it's called that. And there's another quantity, sigma ij, which is actually a half. It's a little complicated to write, but there's a reason. And the reason is that it's traceless. This is not good. Ij. This term is actually proportional to the expansion, but I subtract it so that the trace of sigma is 0. If I've done everything right, then I believe this is, so sigma, trace sigma is 0. And this is called the shear. And there are nice diagrams in the literature which explain geometrically what the shear is. So the expansion is when geodesics come out of your surface and they either bend towards or they bend away. Away is positive expansion, towards is negative expansion. Shear is when they come out of your surface and they sort of do different, it's shear. I mean, I don't know a better way to explain it. It's, I think, comes from fluid dynamics, obviously. But anyway, there are nice pictures for this. And now what you can do is simply rewrite this Riemann, this Ricci curvature equation I had, which I had written as R00 equals minus a half del 0 gik dot minus a half minus a quarter gik g dot jk gjl g dot il. This is the equation I shouldn't have erased. And what you can more or less see is that the first term is actually the time derivative of theta, and the second term is a combination of the square of the shear as well as the square of theta. Okay, and when you plug these two things in, you get the very nice equation that R00 so is equal to minus theta dot, that's this term, minus 1 by d minus 1 theta squared minus trace of sigma squared. So that's the shear term, and this is expansion squared and this is expansion dot. There are various ways to simplify it. It turns out that if instead of theta I took 1 over twice d minus 1 of this quantity, then I could collect these two terms into one term. It would just be the derivative of that. Actually, Raychaudhuri was pretty smart to do that. So he defined a g, which for him was 1 by 6 g minus 1 g dot. If you see it in my notes, or I might have time to explain it, it turns out that this quantity is equal to the Hubble constant in the FRW metric. So it's the right thing to do. It just differs from this by a factor 1/3. But since this has got a dot and a square, they combine nicely. And of course, 1/3 really means 1 by 2 d minus 1 if you want to work in general space, dimensional spacetimes. Good. So actually, this is Raychaudhuri's equation. The 0,0 component of the Ricci tensor is minus the time derivative of the expansion minus the square of the expansion minus the trace of the shear squared. And that's it. Now, there's no physics you can get out of this because actually it's just an identity among derivatives of G. Not very exciting, but it's an insightful identity because this is going to satisfy some equation of motion, namely Einstein's equation if we are doing GR, or some more general equation. And so we can postpone. So once we have this, now we can use this as the left side of Einstein's equation. Now, Einstein equation, as you know, has an r mu nu minus half g mu nu r, the Einstein tensor, but you can invert it to get R mu nu equals 8 pi g T mu nu minus, so this is like the trace reversed version, and then I'll just include the cosmological constant here also, then that is 2 over d minus 2 to g mu nu lambda, and lambda is of course positive for de Sitter type and negative for anti-de Sitter type, and that's R mu nu. Now we can combine this with that and we get some equation which tells us the expansion and the shear in terms of matter and the cosmological constant. And that's the thing that normally is thought to be the Raychaudhuri equation. And so what we get here is yeah, I have a feeling I didn't, I was, yeah, okay, it's here. Good. Good. So this equation, so combining these two equations, we get theta dot plus 1 by d minus 1 theta squared is equal to d minus 1. So this is on the other side. There's a minus trace sigma squared. Okay, so I'll write it, sorry. Theta dot is equal to minus 1 by d minus 1 theta squared. Then there's minus trace sigma squared. And then there's minus r00. I've just taken theta dot to this side. And now I have to put this stuff. And with this stuff I get that, okay, first let me write this for 0, 0. So this is 8 pi g. This quantity I'm going to call t hat 0, 0. And then twice over d minus 2 g 0, 0 lambda. And this in my conventions, this is minus 1, so it's that. Right? So this contribution then is minus, actually there's a bracket, 1 by, sorry, I'm really messing this up. I'm getting a bit tired by now. Let's get it straight once. It's a very simple equation. 1 by d minus 1 minus theta squared minus trace sigma squared. I think I did a mistake here. Well, there's a mistake somewhere in my notes. It's either here or here, but it won't change anything much. And then minus 8 pi g t hat 0, 0. That comes from substituting r 0, 0. And finally, plus lambda. So this is also known as the Raychaudhuri equation, and it's a better one in a sense, because now we have the expansion in terms of the derivative of the expansion in terms of the expansion, the shear, the matter contribution, and the cosmological constant. And now everything depends on what's the sign of the right hand side. And now the sign becomes very important, and we see that this term is nicely negative, so it's telling me that theta dot is negative. This term is nicely negative because sigma is a real matrix and I've traced the square. This term may be anything, so I have to impose an energy condition. And the energy condition has to be t hat 0, 0 greater than 0, because I want to get a bound. So of course there's no guarantee this energy condition is valid, But if I impose this, so this is okay. This is called the weak energy condition. Sorry, the strong energy condition. Sorry, did I do something? Yeah, the strong energy condition. So only imposing that T was positive is the weak energy condition. T00 is positive, but if T00 minus this stuff is positive, then it's the strong energy condition. And there's an amusing fact, which is that neither the strong energy condition implies the weak energy condition nor the other way around. So it's in a sense it's stronger, but it's not stronger in the usual mathematical sense. It doesn't imply the other one. But for this equation, we want this condition. Now, you may question as much as you like whether this is true. The point is that we are going to get consequences from this equation only if this is true. If it's not true, we don't get consequences. End of the discussion. Okay. And finally, lambda. Well, you see that if it's of ADS type, then we are good. This is also negative, and then with these two conditions, everybody is good. But if it's of de Sitter type, positive, then there's a positive term on the right side, and you have to hope that this term in magnitude is just so much smaller than everything else. Okay. Now, once this is done, you have a very nice conclusion. You get an inequality which you can solve. So you get, so with all the conditions, and there are really, okay, one thing, in case you do read the original paper, there was one more term called rotation or vorticity. That I have removed because my geodesic congruence is orthogonal. If it was a non-orthogonal geodesic congruence, I would have got one more term, and it actually seems to go the other way. So it's actually very convenient to work only with orthogonal congruences, then no rotation term. So this is one assumption, and lambda less than 0 or small is the second assumption. Okay. So with all these assumptions, theta dot plus 1 by d minus 1 theta squared is less than 0, and you conclude that theta minus 1 is greater than or equal to theta 0 minus 1, where this is an initial value, plus 1 by d minus 1 t. And so if the initial expansion is negative, so theta 0 is the expansion at time t equals 0 on my hypersurface. If theta 0 is negative, then clearly theta inverse goes to 0 within a time d minus 1 of order d minus 1 over the magnitude of this. Okay. And that's pretty much what we have to say about this. So theta inverse goes to 0, and that means what? That means actually that the metric must diverge, must go to 0, because it is actually has G inverse times G dot, and you can show that it's not G dot going to 0, so it's actually G inverse going to 0, G inverse going to infinity, so G is going to 0. And so this is the condition for a focal point. And the last thing I want to say is that there's a nice interpretation of theta itself. So what you can do is from FRW metric, you can, wow, I really went way over time, I'm really sorry. From FRW metric, we know that det of G in this metric is equal to A times 2 to the D minus 1, where A is the scale factor. So from this it follows that the Hubble constant, which is A dot over A, is equal to just 1 over D minus 1 times theta. So we learned that in the FRW metric, the Hubble constant is the same as the expansion, but there's a crucial difference. The Hubble constant is really constant in space. It only depends on time, but this depends on x and t. So, in the FRW metric, it happens not to depend on x, but in a general metric, you can call this the local Hubble constant. It's like the Hubble constant in a finite region of space, and it's that constant which, if it has a certain sign, then it will lead to focusing. Now, in the next lecture, I'll make it clearer. I think this wasn't very clear, whether they focus in, when they focus in the future or in the past, and then what Hawking did to complete this argument and argue about singularities. So, as I said, this argument simply gives focal points in synchronous coordinates and no more than that. So, I'll stop here.